Hello, hey there. This is Surinder. I would like to show you guys present one of my favorite projects from my undergraduate college days, which was implementing the KD trees. I took up this project at a time when I was beginning to be very curious about data structures and algorithms, and I was very interested in fancy implementing fancy algorithms. I was reading up on ways to search in multidimensional areas, and I was thinking of using binary trees, but then a professor of mine suggested this particular data structure to me to use to search in multidimensional spaces. Um, the word k from in the word k in the k dimensional tree in KD tree is actually the number of dimensions. You can substitute k with any number of dimensions that you want. So, uh, uh, for example, 3D trees, 4D trees, 2D trees, any number of trees, and it easily can search for points in those dimensions very easily. The basic idea is that each level of the tree compares against one dimensions and progresses downwards of the tree until we find what we are searching for. So you can see that each level of the tree has a cutting dimension, as in it cuts the space into two. For example, consider the example tree here. The topmost node, the root node is 7, 2, and it has 5, 4 to its left and 9, 6 to its right, and 5, 4 has 2, 3 and 2, 3 to its left and 4, 7 to its right, and 9, 6 have 8, 1 to its left. So the basic property here used here is similar to binary tree, wherein all the nodes to the left of the root are smaller and all the nodes to the right of the root are greater than the root. Uh, but there is one key difference. Each time we move downwards, it is based on only one dimension. For example, uh, all the nodes whose x values whose x values, that is the first values, are greater than the x value are lesser than the x value of the root, are placed towards the left, and all the nodes with x values greater than the x value of the root are placed towards the right. See, for example, 5, 4, 2, 3, 4, 7 all have x values lesser than the x value of the x in the root. And in the second iteration, as in the level, let's consider the root as level 0, and in the level 1, this property is based on the y-axis. So all the elements, for example, 5, 4 has 2, 3, wherein the 3 is lesser than 4, and 4, 7 to its right, wherein the 7 is greater than 4. So using this property, we can easily navigate downwards to the tree and search any element. For example, if we were to search 4, 7, we would first compare it to the x-axis. So 4 is lesser than 7. So we would move towards the left, and then now we would use the y axis property. So 7 is greater than 4. So we would move right, and tada, we have found 4, 7. The runtimes of this particular tree is big of log n for search, big of log n for insertion and deletion, and big of n space requirements. And it is one of the most efficient data structures for searching in range searches, dimension searches, and nearest neighbor searches. Uh, so yeah, that's about it. Thank you very much for listening.